All right. So, happy Wednesday. Today we're going to continue talking about magnetic phenomena. Additionally, as per the email I sent out yesterday, some things have come up. This particular Thursday won't work very well for lab this week. So, it's seeming that the best day that I'm aware of that everyone could probably meet is next Thursday. So presently, it's we won't meet tomorrow. We'll meet next Thursday for our in-person lab instead, and that'll be the last in-person lab of the summer. That day we will do one lab on resistor circuits and one lab on electric motors, utilizing the things that we talk about today and tomorrow. So those will be next week. Let me know as we're nearing that time if next Thursday doesn't work, because I want to make sure to get these labs in. So if there's any conflicts, any concerns, let me know, email me so that I can make sure that we can reschedule and so that we can get these last two in-person labs in. After the next two in-person labs, there will additionally be two out-of-class, out-of-person online labs that I'll give you kind of as independent research. Not even necessarily research, but just independent lab tasks, because they're going to... The last two assignments involve things that make more sense simulated or make more sense as sort of guided independent research questions, because nearing the end we're going to start talking about things like light, and we're already talking about things like magnetism, which are kind of hard to visualize. So we'll meet one more time for two more in-person labs. That'll be labs 7 and 8, and then after that I will give you, as we near that time, I will also make available to you through email and on the Brightspace page 2 extra labs, and you can do them whenever you want on your own time. I'll need them graded to me by the end of the summer term. More details on those as we get closer to them. For right now, no lab tomorrow. Yes, lab next Thursday. Let me know if there's a conflict. What that means for this week is today and tomorrow and Friday will be just wrapping up chapter 1920, the stuff on magnetism. I imagine we'll get through the bulk of the material today, so Thursday and Friday will be small amount of wrap-up and homework questions day. Do make sure to come to at least one of those 2 days to make sure that you get the last pieces of material. But as we get near the end of the chapter, we'll have at least one homework day for everybody. And then next week will be test prep. Test 2 will be all the electricity and magnetism stuff, chapters 15, 16, 17, and then the bits of 1920 that we're doing right now for magnetism. We'll have at least one day next week to meet up and talk about the study guide, go over things, at least one study day, and then the test will launch about next Wednesday, and it'll work similarly to the first one. After that's in, we'll talk a little bit about light, and then we'll have a similar study period before the exam. Again, let me know any questions, needs, concerns, etc. as you have them. I'll give you guys a second to chime in if you need anything, and I'll be getting the presentation for today started while that's happening. So, yesterday we left off talking about the fact that, sort of going into some of the ways, some of the places that magnetic fields will act on charges moving through the magnetic field. I looked at the example of particles being fired into a field by themselves and then kind of turning perpetually as a result of the force from the field changing directions. We also looked at what would happen if you ran electric current through a magnetic field that was perpendicular to the direction of current. Namely, magnetic fields can exert forces on wires as long as the field is perpendicular to the direction of current flow. And this can be kind of a problem for modern electronics if magnets and magnetic fields end up in the wrong part of the circuit. They can literally rip wires out of sockets, or worse. The fact that magnetic fields exert force on charged particles can be both a good thing in the case of Earth's magnetic field blocking space dust or in use in mass spectrometry, but it can also be a bad thing in the case of it tearing wires out of sockets. And this is one reason why you don't want to put a magnet anywhere near your computer or your gaming device or your smart TV or etc. But there's another reason that this is a problem. And it turns out that not only do magnetic fields act on electric current, it turns out that electric current creates its own magnetic field in a very strange twist. When you run electric current through a wire, that wire has moving charges through it, so there is a current flow, there is charges moving through space. And as a byproduct of that, by virtue of sending current through a wire, that creates a magnetic field around the wire. All wires with current running through them create their own very small magnetic field. And the picture on the right of the screen here is meant to kind of represent that. Here we have a long conductor being moved directly up and down into a board. On that board are several metal shavings, and as current runs through that piece of metal, it is giving off a magnetic field on all sides of itself, and therefore the metal shavings are reacting to that magnetic field and forming up in lines to represent the field lines. The way that you determine how those field lines work is still related to right-hand rules, although it's a little bit different this time. If you say, have current running through a wire, and that current is going vertically upwards, if you take your hand, like you're going to do right-hand rules, and you curl your fingers inward, basically like you're making a fist, just a little more open. Again, your thumb is still pointing upwards to represent the current flow. If you start rotating your fingers in the direction, if you rotate your hand in the direction that your curled fingers point, you can kind of see kind of a spiral shape showing here. And as you rotate your hand in the direction your fingers point, you can see that that spiral will spin counterclockwise. The opposite of that would be if the current was moving downwards. If you spun your hand in the direction the fingers point now, then the magnetic field would spin counterclockwise. So, bar magnets, stationary magnets, create magnetic fields in straight lines that point from north to south. The field created by wires with current running through them is a little stranger in that it's a circular loop that's constantly rotating the wire, either counterclockwise if the current is physically pointing upwards, or clockwise if the current is pointing physically downwards. It is a very weird situation, but it, again, shows how interconnected electricity and magnetism are. They are separate, but they're very related. Often one can cause the other. Two sides of a coin, basically. And we have a formula for calculating the magnetic field that a certain wire will give off. That formula is right here on screen. B, the magnetic field given off by a wire, is equal to mu. This is a universal this is not coefficient of friction. This is a different use of mu. I apologize for the repeat. This mu, with a subscript 0, is a constant known as the permeability of free space. It's a universal constant. It comes up a lot in upper level physics. It is always a constant perpetual value listed right here. Permeability of free space, mu 0 equals 4 times pi times 10 to the negative 7th Tesla times meters over area. Oh, sorry, that's Tesla times meters over amps, excuse me. The unit's not super important. All you really need to care about for its use in this formula is it is a constant. Its value will be provided for you. You don't have to memorize it. The reason it's being used here is the permeability of free space, just as a physics concept, represents how well certain things are able to move through open empty space within the universe. The speed of light depends on the permeability of free space. Light is the fastest thing in the universe, so its speed depends on how permeable free space is. Free space just kind of represents the universe, like when nothing is in a specific spot. Permeability of free space tells you how easy it is for a field, for light, for something to travel through that open empty space. And in this specific case, the permeability of free space depends on the permeability of free space will affect the propagation of a magnetic field. Fields are similar to light. They kind of exist at the speed of light. They need to be able to move through and permeate free space for the field to actually move away from its source. So that's why it's here. That's why it's important. Again, all you really need to know about it is this constant, mu 0, equals this number. That will always be true. Magnetic field created by a wire is equal to mu 0 times the current running through the wire. The more current in the wire, the more magnetic field it will produce. Divided by 2 times pi times r. And r represents how far you are from the wire in question. The further you are away from the wire, the weaker the field will be. The closer you are to the wire, the stronger the field will be. So the main two things in this formula that determine the magnetic field a wire creates is how much current runs through it and how far away you're looking from the particular wire. There is one additional factor that can affect it, and that's actually if the wire is coated in rubber or not. Because if the wire is just exposed to open free space, then more magnetic field is going to be able to get out and permeate through that free space. If the wire is coated in rubber, that makes it harder for the magnetic field to actually propagate past a certain point. So insulating your wires with rubber does help to cut down on this magnetic field that they create, which is a good thing. We're not going to bother with the calculations for that because they get really complicated really fast. For right now, we're just going to focus on this one formula just to look at the field created by the wire by itself. Now, the fact that this happens is just kind of weird. But since this does happen, since wires do create spiraling magnetic fields as you run current through them, it's something that electrical engineers, people designing circuitry, have to be aware of. Because we mentioned before that if you run current through a magnetic field, there will be some magnetic force acting on the wire with the current in it. And apparently, wires make their own magnetic fields by themselves when current is running through them. So that means if you have a machine or a circuit with multiple wires in it, each of them with current running through them, sometimes the fields of one wire can exert force on one of the other wires in your circuit. Which is one reason why circuit designers have to be super, super careful. Because depending on what wires they have, where they place them, oftentimes what axis the wires are running in, how strong the current through each one of them is, one of the wires in the machine might make magnetic field strong enough to ruin some other part of the circuit. So it's something that they constantly have to be measuring, constantly have to be aware of. Let's look at an example here. We have two wires that are running parallel to one another, and they each have 10 amps of current moving through them. They both have 10 amps moving through them, but in slightly different directions. The top wire will have it running to the right. The bottom wire will have it running to the left for right now. We're going to treat these wires as if they are 1 meter long, and they are separated by a distance of 10 centimeters. So we know the current running through them. We know how long they are. We know how far apart they are. First question, what is the magnetic field each wire exerts at the location of the other wire? So each of these wires, by virtue of having having current pass through it, are going to create magnetic field. And what we want to know is, what is the magnetic field that wire 1 exerts at the location of wire 2? And what is the magnetic field that wire 2 exerts at the location of wire 1? They're both going to create their own separate magnetic fields, and those magnetic fields are going to travel, overlap, and they will exist at the spot of the other wire. We want to figure out what that value is, the strength of the field that either wire creates at the other's location. And since both wires are equally long, since they're the same distance apart, and since they have the same amount of current running through them, they're both going to create the same amount of field at the same distance. So I'm using the new formula from the previous slide. Magnetic field created by a wire is equal to permeability of free space times wire current divided by 2 pi times the distance between two wires. So our permeability of free space constant is 4 pi times 10 to the negative 7th. Our current flow in either wire is 10 amps. Divided by 2 pi times the distance between our two wires, 10 centimeters, is going to convert to 0.1 meters. As a result, both wires are going to create a field strength of 1 times 10 to the negative 4th Tesla at the location of the other wire. So both wires are creating field, and the field from each wire is that strong at the location of the other wire. Both wires are going to be subject to that amount of magnetic field since the current in the two wires is equal. If, hypothetically, one of the wires had a different amount of current, then one of the two would get a different amount of magnetic field. But in this specific case, they are equal. So that's the field that each wire is creating. The next question is, how much force does the field exert on each wire? So that'll be a separate formula. We want to know the force that will be exerted on a wire with current running through it as it moves through a magnetic field. So that's F equals IBL, the other formula from yesterday. So in this particular case, we know a current of 10 amps, a magnetic field of 1 times 10 to the negative 4th, and we know that these wires are both 1 meter long. So 10 times 1 times 10 to the negative 4th times 1 will give us a force of 1 times 10 to the negative 3rd newtons. That would be 1 millinewton, which is not a very big amount of force. That would probably make your arm hair twitch, maybe. But electronics engineers need to be aware of these forces. They have to know that these forces are there, they have to account for them, and they have to make sure that all of their wires are rooted in place strongly such that this force won't interfere with anything. Because if you've got wires running near each other, you kind of can't avoid this force existing. You've just got to account for it in your design and try to make everything as sturdy as possible so that the force can't pull anything out of where it's supposed to go. The last question for this particular example: what direction will the forces point if the two currents oppose one another? What about... so, actually, that's its own question. What direction will the forces point if the two currents oppose each other? So, as the drawing currently exists, the two current directions oppose one another. One's flowing left, one is flowing right. This will affect the direction that the magnetic fields spiral around each particular wire. I'm going to erase these first lines so that I can put on some new ones. Using our slightly modified right-hand rules for this, we'll look at the top wire first. If you hold out your right hand and point your thumb to the right and follow the kind of curled spiral of your fingertips, you'll see that for the top wire, the magnetic field, is going to come out of the screen at the top of the wire and into the screen at the bottom of the wire. Now, this perspective is really just due to the fact that we're operating on a flat piece of paper right now. But because the magnetic field is spinning, it doesn't really have a north-south pole. It just kind of follows itself. The north tail is following the south tail of the constant rotation. That means that the field on either side of the wire is slightly different, or the direction of the field is slightly different. Above the wire, all the field lines are coming out of the page. On the underside of the wire, all the field is going into the page, and that's going to keep spiraling around in that shape as long as the current is flowing. Meanwhile, for the other wire, your thumb's going to point in the opposite direction, so that means that your fingers are going to spiral in the opposite direction. So for this wire, magnetic field will go into the page above it and come out of the page beneath it. So the direction of current flow has affected the orientation of each specific spiraling magnetic field created by each wire. This is going to affect what direction this force we've calculated, the 1 times 10 to the negative 3, is going to point in, because the direction of the field determines the direction the force ends up pointing. So, let's just look at this from one wire's perspective at a time. Let's start with the top wire, where the current is pointing to the right. The top wire is not going to be affected by its own magnetic field. That's a convenient fact that you can remember. A wire is not in any way, shape, or form affected by the magnetic field that it itself is creating. You can keep that in mind. You don't have to worry about trying to figure out what a wire is doing to itself because of its own magnetic field. So wire 1, up top, is only going to be affected by wire 2's magnetic field. And from wire 1's perspective, the field from wire 2 points into the page above the wire, and that's going to be true no matter how far away from the top of wire 2 you go. I could keep drawing these X's all the way up to wire 1, because at every spot on this page above wire 2, if you keep following the curl of your fingertips, the field from wire 2 is going to point into the page if you're vertically above that wire on the page. So from wire 1's perspective, the field from wire 2 points into the page. So if you take the old right-hand rules, the classic version for when we were looking at F equals QVB, the current flow points to the right. The field is going to point into the page, and then that means that the force is going to point vertically upwards. I'm going to re-angle myself so that you can see my hand position better. Oh, this is not a comfortable way to bend my hand. So, current points to the right. Field, which is the direction your palm points into the page. So the force, the magnetic force from the second wire is going to point up. This will be mirrored with wire 1's effects on wire 2. Notice that from wire 2's perspective, it's beneath wire 1, and every spot beneath wire 1, wire 1's magnetic field is going to point into the page as well. So the entire zone between these two wires has a bunch of magnetic field pointing into the page constantly. So from wire 2's perspective, the field it's subject to also points into the page, but the direction of current has been swapped for wire 2. So for wire 2, current points to the left, magnetic field still points into the page, so palm points into the page, and force, magnetic force, points down. So, while the currents oppose one another, when the currents oppose each other, if the wires are running parallel and the currents point in opposite directions, then the force between them is going to oppose one another. So it's kind of like the north portion of each spiraling field is affecting both at the same time, and they're going to repel as a result of that. So if the currents oppose each other, the force will be outwards. The two wires will push away from one another. They will push apart. This is, again, inverted if you switch the direction of current for one of the wires and the current was flowing in the same direction for both. I'm going to draw what that would look like separately further down the wire. Let's keep the top one the same for consistency's sake. But we'll flip the bottom one if the current was moving hypothetically in the same direction as current 1, then its spiraling field would be oriented the same way. That has flipped completely the orientation of wire 2's magnetic field. So now, wire 2 is exerting field out of the page above itself, like how wire 1 is, and that means that wire 1 will be getting an outward pointing field from wire 2. Again, this outward field would propagate all the way up to that first wire. So now that wire 1 is getting an outward field, if we do right-hand rules again, current to the right, magnetic field out, that force would now point down towards wire 2. Meanwhile, for wire 2 itself, wire 1's field didn't change, so the field that wire 1 exerts on wire 2 would still point into the page, but the direction of wire 2's current changed. So now its current points to the right. It's the magnetic field acting on it points into the screen. So now the force on wire 2 from 1's magnetic field points up. So by inverting one of their currents, we've swapped it to where the forces will point inwards. Notice that in this orientation, they're both getting a different direction of magnetic field from the other. Wire 1 will exert an outward pointing field. No, that's inward. Wire 1 will exert an inward pointing field on wire 2. Wire 2 will exert an outward pointing field on wire 1. They're opposites. That's like the north and the south poles of a magnet, that is. And so, in this case, where the currents are moving in the same direction, those two wires will be attracted to one another. So the force will be inward if the current between two wires is the same. So two parallel wires, as long as they both have current running through them and that current is parallel, they're both going to exert magnetic field on the other, and they're going to therefore exert magnetic force upon the other. That force will point outwards and be repelling if the currents oppose each other. That force will attract and pull inwards if the currents are in the same direction as one another. Again, this whole principle is kind of a headache for electricians and circuit designers because they have to be constantly aware of this as they're designing circuits. They have to, like, depending on the circuit they're designing, sometimes they have to actively know at any given moment what direction current is flowing through a specific wire so that they know what direction of field it's creating so that they can adjust what it's next to, what direction that the wire is running in, so that they can kind of keep its magnetic field from interfering with other parts of the circuit. We might be able to get through the rest of the concepts needed for the homework today. So that's going to be my main goal. We might end up talking a little bit past 11, but we might get through all of them, and then we can have tomorrow as a homework day, and then Friday, we can start talking about the test. Sorry, that was a lot of information. Let's just keep going for now. See how much we can get through today. So, this phenomenon can be very annoying. I've spent a few minutes talking about why it can be annoying. But, kind of like how we've been able to use the fact that magnetic fields interfere with the movement of charged particles, we've been able to figure out a way to make use of this particular fact as well. And that's actually in the case of electric generators and electric motors. Because it turns out that... Sorry, let me rewind. Because wires with current running through them create their own magnetic fields, they then become susceptible to magnetic fields. So by running current through a wire, that wire is now basically a magnet. It can be affected by other magnetic fields. And what we've been able to do with this information is we've taken shapes. We've taken shapes of wire loops, basically. So this image on the left of the screen is a circular current loop, and the shape on the right here is a square current loop. The exact shape doesn't quite matter, but if I was to try to show physically what someone would build for the purpose I'm about to describe, they would take some wire, bend it into a circle loop several times running over itself so that the current running through this particular piece of wire would loop around in a circle several times. So the loop pictured here in this picture would represent a wire loop with current running through it. And with this particular shape, if you send current through this wire, current is going to enter the loop and spin around a few times. Now, how did I bend this? When you bend wire into a circle like this, and this might actually be even more obvious if I was to use this square over here instead. Notice that at every different part of the loop, whatever shape it is, a square or a circle, what have you, the current is going to point in a different direction within that particular loop. Using the square, just because the right angles might make it a little bit easier to see, on the bottom part of this particular wire, the current is going to point to the right. On this wall, it's going to point upwards. On this wall, it's going to point to the left. And on this wall, it's going to point down. On every different side of this sort of repeating square loop, the current is going to point in a different direction. If you were to then, and that's true of the circular one too. In the circular one, if current flows into the loop this way, it would point to the right on the bottom of the loop. And then as it loops around, current would point to the left on the top of the loop. So if you build loops like this, the current is going to point in different directions, even for this one object's single shape. Since the current points in different directions, if you were to put these shapes inside of a magnetic field, say again, using the picture here on the left as an example, we've got a circular wire loop in this, the vertical black lines here represent the magnetic field shape. So these vertical black lines, we have a magnetic field that points vertically upwards, and we've placed this circular loop inside of it and sort of running current through that loop. Now, I'm going to redraw the circle down here because the picture up here, it's already started spinning and the geometry might be a little harder to track for that reason. So I'm redrawing the loop down here. And we've got current running in different directions on each... Oh, sorry, needed to use different arrows there. So for this particular loop, in this particular field, since the current is running in different directions on different part of the loop, that means that the force from the magnetic field is going to point in different directions on different parts of the loop. For this top part of the loop here, if its current points to the right, so I'm trying to use my right hand rules here again, current to the right, magnetic field upwards, that part of the loop is going to have a force pointing out of the board on it. But on the underside of the loop, where the current instead points to the left, magnetic field up, the force is going to point into the screen instead. And what happens if you have any shape and you have one force pointing in one direction on one side and a different force pointing in the other direction on the other side, it starts spinning. And then I drop it. Any object, if you mount it in place in the center, so you've got it like affixed to a bracket, a pivot where it can swing, if you've got one force pointing in one direction on one side, and then on the other side, a force pointing in the opposite direction, it's going to start spinning. It starts rotating. It only stops spinning if force points in the same direction on both sides. So if I was to push down on both sides of this pen, it wouldn't start spinning. But if I point up on one side and down on the other, then it will start rotating whilst mounted in place. It'll spin on its mounting here. So a long time ago, scientists figured out if you run a coiled wire loop with current through it inside of a magnetic field, that coiled wire loop is going to start spinning. Because as it spins, the force acting on it is going to constantly change directions. Well, for starters, when you put it in the loop in the first place, when you put the loop in the magnetic field in the first place, then it's automatically just going to begin spinning because, again, opposite forces on either side of an object that can rotate They create torque in the same direction, and then it's going to start spinning. And then as it's continuously spinning, the direction of current is technically changing, because as the loop physically spins around, the wires are now pointing in different directions, so the current is also going to, again, point in a different direction. The direction of the force is able to keep changing such that, if built correctly, the loop is able to keep spinning. This is the foundation of all electric motors. An electric motor is designed such that if you put a circular or a square loop with current running through it inside a magnetic field, that loop will start spinning. And the purpose of an electric motor is you feed electricity into it, and that electricity runs through a loop inside of a magnetic field. There's physically magnets inside of most electric motors. And that is what creates the spinning effect that the motor is known for, that the motor is meant to accomplish. So that's how we've been able to create a motorized machine using electricity, using this phenomenon. And this is still because of the field that the wire itself creates when you run current through it. Since it's creating its own field, it's now basically a magnet, and it's responding to the magnetic field of the permanent magnet that's a part of the device, just responding to the field inside of the machine. And this field only exists when current is running through the wire, which means you're able to turn the motor on and off. If you stop the current flow, the wire's not making its own magnetic field anymore. It's not a magnet anymore, so the motor stops. You're able to turn it off by deactivating the electric current, which is important. If you couldn't turn off an electric motor, it probably wouldn't be super useful. So, yes, the magnetic field created by wires has the potential to be a huge pain, but it's also what lets electric motors work. So it's actually super useful as well. The formula that we are going to use to describe this particular concept, what we would measure about a loop that is spinning inside of a magnetic field is the amount of torque that is currently acting upon it. Torque is the angular counterpart of force, therefore torque is basically the force that makes things spin. So if you've designed an electric motor that generates more torque, it's able to make something spin faster. All electric motors, they just create spinning. And any machine that uses electric motors either has spinning, rotating parts, or it has some sort of a mechanism or gear exchange design that lets the spinning turn into whatever other motion the machine needs. So all electric motors generate torque from electric current. And the torque that any given motor can create, so again, lowercase tau, this is the symbol for torque. The torque that a motor can generate is equal to the current running through the wire loop inside of the motor times the cross-sectional surface area of the loop. So again, if you create a big circular wire loop inside of your motor, the area here would be the literal circular area of the inner circle formed by that wire loop. So that's the A part of this formula. So current times area times strength of the magnetic field, that's the field that the loop is inside of, and times N. N is the number of loops in the wire. We will demonstrate this in lab next week when we'll actually build a sample electric motor. The main thing to note right now is the more times you coil the wire over top of itself, the more torque that motor, that coil can generate, because the more times the wire's coiled over itself, the more times the current sort of laps back around over top of itself. So it's not really increasing the current, technically, but it is increasing the amount of moving electricity that is present inside of the loop. There's physically more space for more electricity to exist, so it acts literally as a multiplier. If you just had one wire circled around here, then that would just be the current one time. That would just be an N of 1, a multiplier of 1. But if you double wrap the coil so that it's 2 layers, that's twice as much wire with current running through it, so that's a multiplier of 2. You'll get twice as much torque out of it. Every single new loop you add, N increases by 1, and you'll get more torque out of it. So if you ever dissect an electric motor and you look at the coil inside of it, it's probably going to be multiple wires coiled over top of each other into a circular shape. And those are the factors that will affect how much torque a motor can generate. Note that the surface area has to be perpendicular to the magnetic field for this to work right. To get the most out of it, the surface area has to be perpendicular to the magnetic field passing through it. Like, again, our right-hand rules. If this is the flat surface area, then that means the current is spinning through it like this. It's occupying this two-dimensional plane. The magnetic field has to be perpendicular to that plane for it to be perpendicular to the motion of the electrons inside, and that's what will generate the force that creates the torque. As it begins spinning, technically, the amount of surface area that is perpendicular to the field does change. So once it starts spinning and it's no longer oriented vertically, that's less surface area that's perpendicular to the field. So the amount of torque does kind of fluctuate as the loop goes through its different positions. But we're going to be using this formula to try to calculate the highest amount of torque it's able to produce when it's working optimally. So as a quick sample calculation, here we have a wire loop. Where's my cursor? Oh, I see. That's why I couldn't notice it. Here we have a wire loop. It's occupying the XY plane, and it's going to have 2 amps of current running through it. Its radius is going to be 1 meter across, so it's a very big loop. And the magnetic field passing through it is going to be half a Tesla, but that magnetic field is pointing 30 degrees away from the z-axis. So, if our wire loop was occupying the XY plane, the magnetic field would need to be in the z-axis perfectly to be perfectly perpendicular to it. Right now, in this specific case, the magnetic field is actually pointing this way. It's not perfectly perpendicular. That means that we're going to have to use a tiny bit of trig to figure out what portion of the magnetic field is properly perpendicular to the surface area of our loop. But with the information that we have about this, we're able to calculate... Oh. Did I give an N? All right, it's just a single loop. I'll get to that in a second. We have enough information to be able to figure out the starting torque on this particular loop in its current orientation. Torque is equal to current times area times magnetic field, perpendicular magnetic field, times number of loops. We know what our current is. That's 2 amps. So we'll plug in a 2 for current. For area, we'll need the surface area of the circle the loop forms. Area of a circle is pi r squared. So for area, I've plugged in pi times our radius of 1 squared. That would really just be pi. Next, we need to figure out how much magnetic field is perpendicular to our loop area. We know that there is 0.5 Tesla pointing at 30 degrees away from the perpendicular z-axis. So I've drawn a quick little triangle here showing the 30-degree difference between our hypotenuse of 0.5 Tesla and our vertical axis of currently unknown Tesla. I used cosine of 30 degrees. Cosine is equal to adjacent, which from this perspective is our perpendicular leg, divided by our hypotenuse, which is the full at 30 degrees 0.5 amps. And that tells us that the perpendicular portion of this particular amount of magnetic field in its current direction is 0.43 Tesla. That's the amount of field that's currently perpendicular to the loop's surface area. That value does change as the magnetic field changes direction or as the loop starts rotating. But right now, that's the field that is perpendicular for our current orientation. So that's the amount that we will plug into our formula. Lastly in the formula is n, that is the number of loops, the number of times that this coil repeats over itself. And in this particular question, we just have a single piece of wire circled around, so that's just an n of 1. It isn't lapped back over itself at all. So all those things multiply together, current times circular area times perpendicular magnetic field times number of loops, give us a torque of 2.72 Newton meters. If you haven't used or thought about torque in a while, that's okay. The unit for torque is Newton times meters, because it's force exerted at a distance from a fulcrum to make something spin. And that would be the torque of this particular motor. We could make this motor more powerful by running more current through it, making the loop bigger, making the magnetic field stronger, and creating more loops in the coil. So the most powerful electric motors make use of all of those things. They have high current, big loops, strong magnetic fields, and the coils are looped over each other several times. The physically smaller you have to make the motor, the physically weaker it will be, because you've got less space for wires and current and all that. Now, as this particular loop starts rotating, if this wire loop is allowed to spin around the x-axis, where will the torque acting on it be 0? Now, this particular loop is going to start rotating. It would be like you were spinning a hula hoop in your hands. And this particular loop, the torque on it would be 0 as the loop lines up to be parallel to the magnetic field. So if the magnetic field points this way, and our loop normally points this way, the loop will start rotating until it's parallel to the field. At that moment, the torque becomes 0. Because at that point, the field is no longer perpendicular to the area, and you don't generate any torque anymore. Designers have to be very careful about how their motors operate around that particular point of their design. We'll talk about some mechanical ways to try to avoid the problem of it hitting that point and stopping when we start building some motors together next week. But that is the basic science for electric motors. And here, actually, just to kind of show you what that might look like physically inside of an actual motor, here we have an actual square coil inside of a magnetic field that is allowed to spin when current is run through it. So this is what like an actual constructed motor that you might buy for some apps, for some appliance, would have inside of it. All motorized toys have this. Electric cars have big versions of this. Your cell phone actually has one of these in it too. The vibrate function on your cell phone, how that works is it's basically just this with a weight attached to one side of the output shaft of the motor, such that when the motor spins, that weight is kind of spun and thrown around in a very odd way, and that creates kind of a weird torque that makes the whole phone shake. So, electric motors are everywhere. Anything that moves because electricity runs through it, it's due to this. It's due to this basic machine.
So it's pretty important. And it's, again, applied thanks to all the concepts that we've talked about thus far. So, despite how weird magnets are, they're pretty important to the way that our entire society functions. So, magnets. Alright, that's mostly everything that I wanted to actually show you. That's most of the content that will be on the Chapter 19 homework. There's only one more brief concept that I just want to go ahead and show you just to get it out of the way. And that's the idea of magnetic flux. There's a single question on the homework that deals with this. It's just a quick math question, and this is the formula to use for it. Magnetic flux is it's a measurement of how much magnetic field passes through a perpendicular surface area. So the picture is presently shown here on screen. We have magnetic field passing perpendicularly through a flat piece of paper. This generates a certain amount of flux. This symbol here is the symbol for flux. Flux is defined as the perpendicular magnetic field passing through a certain amount of surface area. This is a multiplier. You multiply magnetic field by the surface area that it's passing through. If you'll notice, we basically just did that in the torque formula. So this concept, this idea of magnetic flux, is part of what makes the motors work. You need the magnetic field to pass perpendicularly through the surface area of your wire loop. It's the same thing here. The flux is just a measurement of how much magnetic field passes perpendicularly through a surface area. And we measure flux because flux is kind of the thing that it's the part of magnetism that affects objects. The more flux generated, the more effect that magnetic field is able to have. Notice that if you tilt this particular piece of paper such that it's no longer perpendicular to the magnetic field, you get a smaller answer. There's less field perpendicular to the paper, and there's less flux generated, so the magnet doesn't have as much of an effect on that particular object. So the concept of flux, we're just using it as a way to quantify how much field passes through an area, how strong the effect the field acting on that area will be. There's just a single calculation that directly asks you about flux in the homework. You just want to multiply B times A. That's all it takes. And that is magnets and all the information that we're going to need for them to be able to do Chapter 19 and 20 homework and for the test that is upcoming next week. That's a lot of information for today, so we'll call it here unless you guys have specific questions. If you have questions, I want to know what they are now. But with all that said and done, if you don't have questions right now, we'll have our break for today. I'll be here if you have questions, if you come back with them. Be working on your homework, be looking over it. We'll call tomorrow officially as a homework day so that you can work on it, or come back with work on it, pop in if you have questions, email me if you have questions. Friday, I'm going to aim on Friday to start talking about what the test will be like, start going over study materials for the upcoming test, but it'll still be kind of lightly focused on homework. We'll talk about the test and the study guide, and then I'll set you back loose to work on homework and study stuff. Test itself will be next week. Again, it'll work very similar to the last one. I'm kind of rambling at this point, and I've done enough rambling today. So if you have questions, stick around and let me know. But if you don't, I will see you either today if you hop back in with questions, or I will see you later this week. Have a good one.